Very good. Yeah.
Let's start.
Okay.
Okay. Good morning, everyone. I was super impressed how energetic Matt is at 11 o'clock in the morning. I'm not sure I can have the same energy level at 10 a.m. in the morning. It's great pleasure to be here. It's first time in South Africa, and I've enjoyed a week of kite surfing on the beach. It was fantastic. So this lecture is about effective field theories. It's actually effective quantum field theories. Of course, you're now very well prepared by Matt's lecture, but maybe I should, just for my own reference, how many of you who has had a quantum field theory lecture or course? Now, all of you because of Matt, but maybe beyond Matt's lecture. Heribert hasn't had one. 1, 2, 3, 4, 5. So about half of the people. So I'll try to work around this a little bit for those who haven't had it. It's always sort of a narrow path. At one point, I was teaching some middle school kids, high school kids, and I was talking about the logarithm, and somehow everybody in the audience, I could see they were uncomfortable. They started speaking to each other. And after 5 minutes, somebody said, "We don't know what this logarithm is." And I said, okay, I'm very sorry. Then the next lecture, I had to something with the sine function. So I said, "Do you guys know what the sine function is?" And then they again were very unhappy. So you think you're idiots and don't know what the sine function is? So it's a very narrow path. So don't be insulted if I explain something which you already know. Then you should feel proud of yourself. On the other hand, also don't be shy to ask questions if I say things without explaining or which are things you haven't known before. Good. And so the general motto maybe, so I can go over this schedule here that I put up on the screen. So I put 5 lectures here. I think not all of them are the same length. We'll just go from one topic to the other as we go. Today will be a little bit of introduction, sort of the basic terminology. What is a low energy effective theory? What are the basic steps in constructing such an effective theory? One concept that will be important is what is the dimension of an operator. So Matt talked about Lagrangians, and we'll write down very long Lagrangians, and we have to order terms, and then it will be important to know what the dimension of these different terms are in a Lagrangian. And then in lecture 2, we'll go to a land called Photonia by the reference which I'm quoting here. So we go to a world where we live at very, very low energies and where we don't have enough energy to produce a positron electron pair or anything. So we do physics at very, very low energies. And then the question is, what is the right theory to do physics there? All we have is photons. And so then we want to write a Lagrangian. This Lagrangian will only have photons. This is an effective field theory of photons, and we'll see what we get. One interesting thing to analyze with this is the scattering of photons. This may be already a question for the audience. Do photons scatter on each other? I should have asked Heribert for 2 laser pointers, so we could take the 2 laser pointers, point them at each other.
They shouldn't.
They shouldn't, somebody said, if I heard it correctly.
Yeah, they shouldn't.
The answer is kind of correct. Indeed, if you've ever had 2 laser pointers, you'll find that you will not observe any scattering. The light just goes through each other. But it's actually not quite true. So when you do quantum field theory, you can draw diagrams where a photon interacts with a photon. So this is a scattering. So this is really an interaction of 4 photons. And the question is this a big interaction or a small interaction? And this is something one can understand in this effective field theory. And we'll find that it's a very small interaction, and we'll be able to explain why this is the case. And we'll learn some basic things like how to organize terms, etc., how to write down this Lagrangian. The hidden agenda between this world where we only have photons is our own world. So this last point is the standard model effective theory. There could be many other particles around that we can't produce at our low energies that we have here, where maybe the LHC is not strong enough to produce these. And then you can write down an effective theory called standard model effective theory. And it's pretty analogous to this, this photon effective theory, conceptually almost the same, but then instead of having 2 operators or so, or 3, you'll have, depending how you count, 60, 70 operators. So it's more complicated. This we cannot do in detail, while for the QED at low energies, we'll be able to do it. Then lecture 3 is maybe the most technical one, where I want to do an actual computation. Matt mentioned that one can sum logarithms with certain equations. He wrote down some series that he wanted to sum. And the technique to do this are so-called renormalization group equations. And this renormalization is an important concept in quantum field theory, but it's also kind of a non-trivial concept. So I'll try to walk you through it. This we'll do with an example from flavor physics, where we discuss the weak decay of down into an up quark. And then we'll get to modern effective field theories. And I'll again, at the end of the day, maybe we'll want to go to the LHC, but I'll again do QED. And I'll use this effective field theory to derive a factorization theorem for electron-electron scattering. This electron-electron scattering, these electrons radiate a lot of soft photons, and they have a particular structure, and one can write the factorization theorem for them. This is in principle a very old story. In 1960, this was one of the first factorization theorems that was understood, but we can derive this very nicely with these modern methods. And then this would lead to soft emissions in QCD, which have a similar but much more interesting structure. And depending how far we go, we come to research where Heribert has made important contributions, namely this resummation of certain logarithms in jet processes. And this also relates in an interesting way to the small x physics discussed by the other lecturers. But in principle, this agenda is not really set in stone. So the motto will be something that a colleague of mine always says at the beginning of his lectures: it's better to uncover a little than to cover a lot. So I'm happy to adopt if you say at one point, well, but this wasn't clear, or we should do this or that, then we'll just change. So in the best of all worlds, you'll ask so many questions that we never make it to lecture 5, which will be perfectly fine. Good. This is, I Googled who said this. The quote is by Vicky Weisskopf. And then when I Googled the quote, there was a drawing of a woman showing her knee. So this is a sexist spin on this quote.
You're being recorded, you know this.
I'm sorry. But so let's get started.
Weisskopf did say this quite a while ago.
But the drawing wasn't by Weisskopf, so I'm not sure he should be blamed for it. Good. So, effective quantum field theory. This is often abbreviated as EFT, effective field theory. And it's an effective field theory is QFT. But this QFT is not valid to arbitrary high energies, but it's valid up to some scale lambda. And sort of the opposite of an effective field theory would be a fundamental field theory, which would be valid to arbitrary high energies. And now, the question is, what are examples of effective field theories? And in some sense, I've already given the answer. Every theory we know is an effective theory. It is clear that if you go to super high energies, interesting things will happen, maybe other particles. It's clear that if you go up to the Planck scale, something with gravity should happen. So basically, any quantum field theory you write down should be viewed as an effective field theory. And in some sense, at one point, we should change the entire quantum field theory curriculum to teach it as an effective field theory. Also, for example, the standard model. We know that the standard model is not the fundamental theory of everything, even though it's extremely successful. So it's not, if it's not valid to infinitely high energies, we should treat it as an effective field theory, work with it as an effective field theory.
We did your PCDs the effective field theory down to a certain scale.
No, the idea is always these effective field theories are down, they're fine. It's up where they run into problems. So for QCD, of course, if you go to higher energies, all of a sudden you see all these other particles like Higg's W boson sets. So you can say QCD is a low energy effective theory for the entire standard model, or maybe QCD plus QED together is a low energy effective theory of the standard model. But what of course can happen is that things get interesting at low energies. So if you just take the QCD Lagrangian, in principle, this is perfectly fine to arbitrarily low energies, but the computations will get tough and tools like perturbation theory will start to fail. But it's not QCD's fault, it's the perturbation theory fault. Also, this terminology of effective theory versus full theory, this is used in a bit, for example, sometimes you say chiral perturbation theory, which is an example of an effective field theory. You say this is a low energy effective theory of QCD. So then you view QCD as the high energy theory, as the full theory. But of course, it's also not the full theory. At even higher energies, you need the full standard model. So what you can have is some tower of effective field theories, where so you go from one theory to another. And in some sense, with our photon effective theory, this is sort of the lowest energy effective field theory you can have. And then if you go higher and higher in energy, more and more stuff appears, and you get different and different. So there's an entire tower, and you can always view the next one as sort of the full theory for the effective theory. So that is the basic idea. And what is important here, and maybe a bit more formal than this statement, is that these effective field theories, they implement an expansion. So there's a systematic expansion, some expansion parameter, which is the energies at which you're doing your physics, divided by this scale lambda where the theory breaks down. And this is important. You can systematically include more terms. You sort your terms. If you want some given accuracy, then maybe there are very few terms in this effective theory, but then you can systematically keep adding things until you have the precision that you want. So what this effective field theory really is, it's kind of the Taylor series. And so the Taylor series is an important instrument that you can expand in scale ratios. It's one of the fundamental things. It's maybe as important as perturbation theory. Perturbation theory, you expand in couplings. Effective field theory expands in scale ratios. And both you can systematically improve order best. We can look at some examples. You've already used effective quantum field theory, even if you haven't used quantum field theory. For example, we could, now I can try to use colored chalk. You could look at the hydrogen atom. And this is quantum quantum mechanics class. So proton, and then of course a naive picture, and then an electron circling around at some distance. Typical distance will be the spore radius. And now, if you look at this closely, then this proton here, this you will learn in maths lecture maybe tomorrow. Already haven't heard about it. So there are up coords in here, down coord in here. Then there are gluons. Then there are virtual pairs. I mentioned S quark and an anti-S quark. So this proton is a super complicated object. There are electrical charges flying everywhere, very complicated. So if you want to compute the hydrogen atom, it looks completely hopeless. So at this point, you should say, well, hydrogen atom is too complicated, I go home. Now you did not do that when you computed the hydrogen atom, because you said, well, it is true that this proton is incredibly complicated, but the scale at which all this stuff is happening, this is a much smaller scale. Again, a bit naively, this is the proton radius, which would maybe be something like a femtometer or so. Roughly the quantum wavelengths of this proton. So there's this very short scale, and then the Born radius. This is I think with a -10 meters. So this is many orders of magnitude larger than this. So there's a scale hierarchy here. There's this large distance here and the short distance here. And when you write down a theory for hydrogen, since there's this large separation, in principle, you don't need too much. All that is needed is, well, you know, it has positive charge. And then you wrote down a Hamilton for this. Electron mass over R. I will, throughout my lecture, work with these actual units. I said H bar and C and everything to 1. Hope that is fine, or we can discuss it. So this Hamilton operator which you used is of course not the exact hydrogen atom. The exact one is much more complicated. So this is really an effective Hamiltonian that you have used. And even in the first term, you see that this is of course not exact. We know that the kinetic energy is really again without factors of c squared. It's the square root p squared plus m squared minus the rest energy. And so then you can expand this p squared over 2m. And presumably I get this wrong, but there's a p to the 4th collection. 8m cubed plus etc. So it's clear that there will be more term in this effective Hamiltonian, and presumably in this quantum mechanics lecture, you may even study the effect of this relativistic correction, so you can systematically add terms to this Hamiltonian to make it more precise. And the typical momentum here of the electron in this atom is of the order electron mass times the coupling. And so you see that there is an expansion here. This is p to the 4th, so it's this thing to the 4th divided by powers of the electron mass. So this term is suppressed, and if you compute it, you find it gives a small correction, and you can systematically continue. How would you would you include corrections to the potential? And ask a little bit simpler. If this would be, let's say these cords would not move, they would just sit there still so that it's a static configuration, then how would you correct this picture that we say it's just a Coulomb potential? Yes.
Did you incorporate the forces like point charges to sort of add interaction terms between the forces?
That would be one thing. If they really would, if it would only be these charges here and nothing else, you could just think the three charges, they would be close together. But I would like to do something like here where I'm not, that would be like writing the full square root, if that would be the true proton. Can I also do some expansion similar to this? Yes.
Can we treat the proton as being able to move as well? So we add a.
Oh, that is the other thing that I'm also, that is of course also missing here. I'm treating it as a static sitting thing, which again is okay because there's a scalarity. This is 1,000 times heavier than this one. So the first approximation is okay. You can take this by changing coordinates and use relative distance. You can take this into account. But let me say it is infinitely heavy and it's some charge distribution that sits there. How can I do an expansion? Yes.
And you can add in the multiple.
Exactly. So classically, there is a similar thing here called the multipole expansion. So you could try to systematically expand this charge distribution and then add this to this effective Lagrange. Now, unfortunately, the hydrogen atom is more complicated. So doing this would not be good enough. And the full effective theory for this hydrogen atom, this is maybe mentioned in this modern effective field theory section. So the hydrogen atom, to write down the effective field theory is kind of complicated. That's why I'm not doing it, or at least postponing it. This was, the corrections here have maybe been looked at already since 100 years, but really a systematic framework to include everything. It's only maybe 20 years ago that people put together all these things. Even before many or all of these effects were computed, but then you needed to be Becher to know how to include some of these corrections. What is subtle, for example, is that if you really do the effective theory, of course, the electron and the proton you can treat as non-relativistic particles, but the photon is still a quantum field. So you have to have a theory which has a quantum theory of photons plus this. And so the effective theory that would be systematically doing this is called non-relativistic QED. So doing this, you can take into account also quantum effects from the electric fields. You can take into effect also that these things move here. So you're not only getting corrections to the potential, but there's also magnetic corrections. And one can do this systematically by systematically writing down an effective Hamiltonian or Lagrangian. Yes?
To make it non-relativistic, do we need to do anything else than change the signature of our metric? Or?
Don't change the signature of the metric.
Oh, not at all.
No, basically you just need to, one thing that is weird and makes this a bit complicated is that you have the kinetic energy. You have this free momentum, which scales like m times alpha. And then you have the energy, the kinetic energy, which scales like m squared, m alpha squared over 2. So it scales like 2 powers of the expansion parameter. Then you have the rest energy, which scales like 0 powers of the expansion parameters. So somehow you have to remove the rest energy, which is fixed. And then in the rest, you have to do an expansion where you expand in this momentum and treat the energy as order lambda squared and the 3 momentum as order lambda. So that is the way to go. And you can use the fact that, again, this is very low energy, so we will never encounter positron. So it's perfectly fine to write a theory only for an electron. You should write this general theory, but it's non-trivial to organize it because you basically have to remove the rest mass from the field and then order by these derivatives.
If I'm understanding correct, that you have then a non-relativistic theory, but still in some Lorentzian metric.
It's a non-relativistic theory for the electron, plus a relativistic theory for the photons, because the photons will still be the usual relativistic thing. That's what makes it kind of complicated. And you, in order to separate out, kind of need to go to more or less the rest frame of these, and then start doing this expansion in the rest frame. So that's why I'm staying away from it for the moment. So this would be an example where you're familiar sort of with the leading power or leading lambda effective theory, but whether it's quite non-trivial to complete. Now, let me do another example, which you presumably also know, and which is conceptually simpler than its non-relativistic theory. And that is the Fermi theory of weak interactions. Somehow my colleagues now decided to call this weak interaction effective theory WEP. But it's a good name. It was always not so clear how to call it, because Fermi, of course, he had the effective theory for the beta decay, but nowadays there are many other things as well. But of course, it's Fermi's idea. I don't know whether it's, at least it's short. Let's look at the following process. So I'm interested in a neutron decaying with proton. So the Feynman diagram, where a down quark goes into an up quark. This it can do. It exchanges a W. Then here I want to have an electron. So this type of process. This is standard model Feynman diagram. So here the standard model is viewed as the full theory. And of course, Fermi didn't know about the W, and nobody had seen the W at that time. So at low energies, instead, you can write down theory which without the W in essence, you simply have this down up. And to go formally from this to this, one has to know the Feynman rule for this propagator here. Exact Feynman rule is not so important, but whenever you have a line here, a propagator, there's always a factor like this, so 1 over p squared minus the mass here. So that is part, if you translate this diagram into a mathematical expression, there will be this denominator that arises from this line here. And this process here, I mean, this is inside a proton, and this proton decays into a neutron. So the momentum transfer here is extremely low. There's almost no energy going through this. And for sure, the energy is the p squared here is always much lower than this mw squared. And so then you can expand this, say, well, at the lowest order, this is 1 over minus mw squared. And then I can add the geometric series squared. So I can do the same type of expansion. And then if you just have a factor like this, there's like, it's like not having a propagator. It's really a prefactor. So we write down this type of operator here, which is the prefactor. So that is this Fermi effective theory. And of course, Fermi didn't know about down and up quarks. All he knew was protons and neutrons. So at very low energies, you will not see these down and up quarks. So you can directly write the theory where you have a neutron going into a proton. So basically the same, exactly the same type of operator, but now directly with protons and neutrons. And these p squareds here, so we will write effective Hamiltonians or effective Lagrangians. we want to write this in a Lagrangian or Hamiltonian. These p squared are derivatives, so we will have derivatives acting on these fields when you write down this correction. Good. So these are two examples. And now there are two types of effective field theories that are used in the literature. One is sort of top-down Wilsonian effective field theory, and the other one is bottom-up. And I want to briefly discuss this Wilsonian effective theory, even though we will not be using it for reasons that will become clear. Now, Matt taught you all of quantum field theory in 2 hours. He talked about canonical quantization. This canonical quantization is not so popular among the people doing gauge theories at the end of the day because it's tough to quantize QCD canonical. It's possible, but not easy. And an easier approach is to use the Feynman path integral formalism. Now I can maybe again quiz the audience who has seen a path integral before. Yeah, many people have, but if you haven't, don't feel shy. Let me quickly show you what it is. We will not really need much of it, but just some the basic things. So in quantum field theory, at the end of the day, sort of all the information we want to get out can be obtained from certain correlation functions of fields. So we have these field operators, and then they sit, it takes a vacuum expectation value, and then I have a field at, let's say, point x1, field at point x2. Let's do 4 of them. There's a T here which says time ordered, and I don't even want to discuss how one gets out this information for now. But from this 4-point correlation function, if you draw this like this, we have these 4 things sitting at different points, and if you can get the 2-to-2 scattering amplitude out of this if you need. It's a long discussion how one does this, but many interesting quantities can be this. And Feynman introduced a different way of doing quantum mechanics first, using this path integral, and the very same method also works for quantum field theory. And basically, what Feynman said is quantum mechanics, more or less anything that can happen does happen. So if you have a 2-slit configuration, then an electron can go one way or the other way, and the 2 possibilities have an amplitude. This amplitude interferes, and then by squaring this, you get the probabilities. And if you have a field, a classical field, this has one solution. It will stay like this, but a quantum field can pretty much do anything. And then Feynman said, well, if you take a given field configuration, then the probability, or not the probability, the amplitude for this goes like e to the I s of phi, where s is the action that Matt has discussed. S of I is the integral d4x of the Lagrangian. And so this is for a fixed one, and then you just have to sum over all configurations, so all convex. And then summing over all of these, each with its phase factor. There's of course a lot of interference and whatnot, but if you sum all of these together, and if you put these classical fields here, at the bottom here, then after normalizing this properly, you get this correlation function out of this. Feynman, in his PhD thesis, did this for quantum mechanics. For quantum mechanics, he said, well, you have to take all possible paths from point A to B. For each path, you compute the classical action, and then you sum over all of these, and then you get the probability that it goes from one point at one time to another point. Maybe to do an intuitive picture in quantum mechanics. So I said if you have a double slit experiment in quantum mechanics, then the particle can either go through one slit to this point or to the other one. Each of these has an amplitude. You sum the two amplitudes, you get interference, you square it, and you get the probability distribution. And Feynman's idea in his thesis was, well, what happens if you do many slits with many of these great things? Yep. Come to the edge of my drawing abilities. If you have this and the particle again goes from this point to this point, now it has very many choices. It can sort of go through this one, then this, and this, and this, and here. Or it can do another path. And it goes here. And so in the limit where you take infinitely many of these things very close together with very, very small slits here, then basically you have to look at every possible path to go from point A to B, sum them all up, and then with the complex, with the phase from the action, you get the correct, you get this transition probability to go from point A. Now, this is sort of for the quantum mechanical case. Now, in field theory, you should think of the same with fields. You start with some field configuration and you end up with a different configuration, and you have to sort of look at all the possible ways, all the possible field developments to go from one point to the other. So it's interesting, in some sense, it sounds kind of intuitive, but at the same time, you see that it's horrible. It must be difficult to define exactly what such an integral means. The key to define it is to actually do what I draw here. You basically discretize things so that you only have a finite number of paths here. And then you have to take the limit where you make this infinitely fine. This is all, it's relatively delicate. People do it in QCD actually, and they numerically simulate this. They use such a path integral formalism, they complete such correlators. They discretize the fields on a little grid, and then they do these sums, and they do an infinite, or not an infinite, a very high dimensional numerical integral to get this. For us, we'll need basically none of this. We only need the free case. The free case one can analyze and one can compute what this is. And then interactions, we do perturbation theory, so we expand them down. And then basically, as long as you do perturbation theory, if you know how to compute the path integral for a free field theory, then you more or less know what to do. But this is very nice because if you construct your effective field theory, all you have to do is construct the Lagrangian. Once you have the Lagrangian, you have the action, and then you get the quantum theory. So it's again a correspondence similar to the one that maps lined out with the Poisson bracket that takes you from a classical theory more or less immediately. So now I can discuss this idea of Wilson. It's maybe the earlier formulation of effective field theory. So Wilson worked with this path integral formulation. And his idea was that if you want low energy physics, then basically the fluctuations at very short distances here should be irrelevant. So you should somehow split this integral into an integral over all the high energy stuff and an integral over the low energy stuff. And then you simply integrate out the high energy part. So the idea is integrate above some scale lambda. Above lambda, this is the high energy stuff. And basically to do this, we take our field. And maybe now we do a Fourier transform so that we can basically sort the different momentum modes of the field, long wave fluctuations and short wave fluctuations. And we will split the field into field with long range, low energy fluctuations and the high energy part. And then you split the field. Then this splits this integration. You now have this low energy integral and the high energy integral. You integrate out the high energy part. That leaves an integral over the low energy part. And then you try to rewrite things in terms of an action for this low energy part. We'll now get a new and effective action. Effective, which only depends on the low energy part.
You want to integrate out phi h.
Yeah, that would be much better. Yes. The high energy part we want to integrate out. And this should be then some effective Lagrangian, which only depends on the low energy part of the field. And this effective Lagrangian here. This will now be super complicated. You've done some complicated integral and you've tried to rewrite this in this form by expanding non-local things. So maybe hopefully there will be a free action of the form that Matt has shown you. And then there will be infinitely many terms here. And these additional terms will come with factors of lambda. So we've integrated out stuff above this scale lambda, and you can order them by this lambda. And of course, there can be several of these terms each order. So that is Wilson's idea. Now, if you look at this integral over all field configurations is already infinitely complicated. So in general, if the theory is not free, then you can maybe only do it numerically, if at all. Doing this separation into the two components, integrating out one and putting it back into this form, this is even more complicated than solving the theory. So at that point, it's easier to just solve the theory than to do this. But still, this is a useful approach because just by looking at these terms, thinking about what terms you can have, you can learn something about this theory. It provides a very nice picture of this renormalization. So you have this cutoff, you integrate everything below, and then you can integrate again, so you can slowly integrate down. And this effective Lagrangian, this is basically the most general thing you can write down because everything will be generated in this integrating out. And what I've forgotten here, what is very important, that there are coefficients that come with this. These coefficients are called Wilson coefficients. How big they are, you will see after you do the integral. But when you slowly lower this, you can see how these coefficients behave. You can discuss what type of behavior you can have. And then Wilson has many nice results what can happen. So if something interesting is if you go to a fixed point, if you start integrating out and this no longer changes, this is something interesting. Or it can happen that certain of these couplings will start to grow and you go somewhere else. So that is interesting. But it's not the way we will do our effective field theory because it's too complicated.
So, one thing that confuses me about this procedure is once you define a scale, you've broken the rest variance. So how do I deal with that?
Indeed, one thing that is kind of nasty is how do you put this cutoff? And this is a problem that Wilson also had. And Wilson wasn't worried so much about Lorentz invariance, but he was worried very much about gauge invariance. Matt will, or depending how far we get, I will discuss some gauge invariance. But yeah, the problem is you can break some symmetries. So what Wilson did is he said it's best to define this theory. He was interested in QCD on a space-time lattice. And in this formulation, he managed to keep gauge invariance exact. But you lose Lorentz invariance if you have this lattice. So in order to compute this path integral, I've already said it, you put a little lattice in space and time. 4-dimensional lattice where the fields live. Maybe the time direction, this is the space direction. And of course, this lattice is not Lorentz invariant, it's not even rotation invariant. But what Wilson could show is that actually you kind of recover this Lorentz invariant. So if you start with a very fine lattice and you start integrating down, there are Lorentz violating effects, but they become small. So it's actually not that big of a problem, this Lorentz non-invariance. In the practical simulations that people do of QCD, this is a problem. So they have to check how big these violations are. Often when they compute the quantity, the result will depend on whether they take it along the diagonal or along this direction, even though rotation invariance, boost invariance will tell you it's the same, and they have to estimate this uncertainties from this. Yes.
Just to confirm, this lattice, like, are you sort of discretizing space-time?
Exactly. So we have little points in the time direction. So T0, T1, T2, T3, and then we have 0, 1 centimeter, 2 centimeters, 3 centimeter. And of course, the goal is to make this as fine as possible. But if you put this into a computer, the finer you make this lattice, the more points you have. At each point, the field can have an arbitrary value. So each of these points will translate into an integral over the field. And so you get many integrals which are evaluated with Monte Carlo methods. So it's a trade-off. Good. So this is not how we will do it. Instead, we'll sort of work from the bottom up. So this is top down, take the full theory, just compute what the effective theory is, but it's tougher than solving the theory. The bottom up approach would basically simply write down what is the most general form of the result. It will involve unknown coefficients, and then you have to have some way of getting these coefficients. Now, the one concept that I now want to discuss in more detail is this operator dimension. Delete the path integral, but there was only this scale lambda here when you did this integral. All the other scales are much lower, and so that's why you get this lambda together with the operators, and then by dimensional analysis, you can read off what power of lambda you have if the operator here, let's say 5 to the 10th or so, has a certain dimension. Then this has to be compensated just by dimensional analysis. So I now want to do dimensional analysis for the fields just to see how each term counts. And so this will now do in nitty-gritty. So let's start with a scalar. And Matt showed you the Lagrangian and the action of a free scalar. In 4 dimensions, you would have d4x. Let's, for the fun of it, use 3 dimensions just to keep ourselves challenged when we do it. And then this is what Matt wrote in the morning. So this is the Lagrangian for a free scalar field. And the goal here would be to read off what is the dimension of this field. And again, so with this, everything is measured basically in 1 unit. For example, I can measure everything in energy units here. So the question is basically this field phi, this should scale dimension-wise as some power of the energy, and the question is what power this is. You know that I times the derivative, this is the momentum. So the d mu here, each component scales like power of the energy. First power of the energy. The x mu here, this is the opposite, the conjugate variable to the momentum. So it scales like 1 over energy. And this here is the action. And I've written this path integral, even though I haven't explained it at all. But e to the is, this s is dimensionless. So this thing here has to be dimensionless. So the dimension of the entire thing is 0. And then we have d powers of this x integral. We said this counts like minus 1 over energy. So if I look at the dimensions, it counts like minus the dimensions of the energy. Then I have 2 power 2 derivatives. So that is 2 powers of the energy. And then I have 2 powers of the field, and I don't know yet what the dimension of the field is. Plus 2 times the dimension of the operator. Good. So what is how does it scale with the energy?
E minus 2 over 2.
E minus 2 over 2. And so, okay, we did it in d dimensions. So it's interesting, for example, if you're in 2 dimensions, then this field is dimensionless. That is, if you're in 2 dimensions, if you do this in 2 dimensions, and if this operator can have basically an arbitrary number of these fields, and you don't get any lambdas here, because it's dimensionless, the field. The derivatives, of course, will still suppress. In 4 dimensions, we have 4 minus 2 over 2. So in 4 dimensions, you've got like the energy. And when we later construct this effective Lagrangian, so if we have 200 powers of the field, that is 200 powers of the energy. And then if the Lagrangian has to have the proper dimension, this has to be compensated by some lambdas. And this will help in the construction because the things that are suppressed by lambda, since this lambda is very high, are kind of small. And so we will, unfortunately, well, fortunately, we will not need operators with 200 powers of the field, but only operators with a small number of. Matt also did the fermion field. Look like this. And you should if you haven't had quantum fields here, let me write this once more. At one point, I gave a quite advanced quantum field theory lecture on the soft collinear effective theory, which is quite complicated. And I had this one student who seemed very bright, but he was asking these very strange questions. In my mind, he said, what is this? This thing crossed out. This gamma, and then I understood he never had any quantum field theory. Somehow I managed to follow, but of course, some of the basic notation just so don't feel. Just ask if I got things. Good. So we do the same thing of the same kind here. This again should be dimensionless. So 0 is equal minus d plus. Now there's one difference here. There's only one derivative instead of two. And then again plus 2 powers up times the dimension of this psi field. Psi field. Except that the 2 has to be replaced by 1, so it's d minus 1 half in equals 4. So that means psi goes like 3 minus 1 half goes like energy to the power. Maybe so. Remember these. Now we can do a quiz, and I can write down operators, and then you tell me what the dimension is. Some operators which we might find in the this was only effective Lagrange. Phi squared is an interesting operator. This is what comes with the mass term, for example. In the scalar case, in the bosonic case, or psi bar psi. What else do I have? Psi to the fourth. Psi bar psi. Psi. This here is an operator with 4 fermion fields. Remember this Fermi theory. Once we took away the W, we exactly had something that had 4 fermions. So this is the operator that would appear in the Fermi theory, however, with 4 different fermions. Down quark and up quark electron. So now for each of those, we can maybe write n. That would be the dimension. And then I want to have this power of lambda that suppresses the terms. These lambdas I've written down for the Lagrangian. Now the Lagrangian gets integrated, integral ddk, integral ddx times the Lagrangian gives the action. So if I want to know this k to balance it, this is just the n minus d. So this is interesting to see which one have a 1 over lambda and which ones maybe have a lambda to a positive. I thought it would be nice to have a break since my own attention span is roughly 30 minutes and we now did 1 hour. It's okay if we do a 10-minute break and then we come back and then we use our knowledge about the scaling of fields to fill out the table here. Good, so we continue 10 minutes. Yeah. Oops, yeah, so we can continue. It's a very confusing school. All the lecturers that are here are called Thomas, and they all are kind of hairy. I say so. And because of all these difficulties, I think the schedule was interchanged, but this is now fixed. But anyhow, maybe more important than who is speaking is just when. So that's great. One thing I remembered in the break is that I forgot to, in this outline, there are a few references at the end, in case you're interested in. One is a website with a longer lecture on effective field series. So this is a 1 semester course. There's also a script on this website, so there's more resources if you want. For this Photonia thing, there's a very nice paper or summer school lecture by Grosin, which I will follow. And then later on for the soft collinear effective theory. Plug their books. For this, I wrote the book, but you don't have to buy it. You can just download it for free from the archive. Anyhow, so there are more resources, many more references in this script, but a few of the relevant references for our discussion would be here. And I can maybe send this outline around to the same email list. Good. I don't know whether there's any questions that arose in the break. Yes.
I just want to ask, what is K? Can you explain what that is?
Yes. But I'm always deleting in this general effective Lagrange. You were writing operators, okay, and some of these operators had factors of lambda to the k.
Oh.
And then there are Wilson coefficients.
Oh.
And I had an additional sum here because, of course, you can have 15 operators which have the same suppression. So some even more. And the reason this is interesting is exactly tells you how many powers of lambda arise here. Because what I have to do to get from the effective Lagrangian to the action is to do this integral d for x, now in d dimension dx of this effective Lagrangian. And this has minus d dimensions from this integral ddx. So this n minus d is interesting because then it directly gives you this. So that is why the k is interesting. Good. And now you have to remember our results. So the phi at dimension d minus 2 half, yeah.
I just want to check, are we just keeping, just saying that lambda has dimension energy?
Yes, yeah, lambda has dimension energy. What I also didn't really explain, so you do this path integral in this Wilsonian approach. And of course, it's a horribly complicated thing. One may ask the question, why can I even write this as e to the I s, some action of this low energy field? The idea is that, well, this low energy theory should still be some quantum field theory and should have some nice properties of quantum field theory. So it should be local. And in a local theory, this action here only involves fields at one point, not fields that are very far apart. Of course, doing this integrating out, you will end up with things which are not at the same point, but then expanding in 1 over lambda, you should get a long series of all these operators. So that's the idea. Good.
Following up on that, so are there any good examples of theories that are obviously non-local? Maybe I'm thinking like the phase transitions, you have correlation that diverge.
That doesn't mean that the theory is non-local, but it can happen that something interesting happens, like that this correlation length goes to infinity. I've mentioned doing this flow a la Wilson, where you integrate out more and more. Some interesting things can happen. And one interesting thing is if the theory no longer changes. So you keep integrating and somehow this theory no longer changes. If you're in some fixed point, somehow the theory no longer really knows about this scale lambda. And this is then something conformal, and you can actually get infinite correlation length. And this is exactly where this very interesting things like phase transitions happen. It's like also the place where sort of real QFDs live.
maybe a more crisp question is there some physics where we have to use a non-local?
Yeah, this local versus non-local is in some sense, it's also a bit how you look at it. So Fermi theory is in some sense, if you say, well, there's the W, so it's in fact, it's non-local in some sense, because there is actually this propagator in between. If you would take the full propagator, it would be a non-local theory. But since your energy scale is so much below the W, then you can expand in a series of local operators. So if you simply integrate out the W in the standard model, and if you now believe that you have this path interval, it would be perfectly fine, integrate it out. And then you have something which is now non-local, at least in terms of, if you look at the fields, you will get fields of different things. It will not have the simple form, but if you do the expansion, you can again expand in local operators. Also in this soft collinear effective theory, you will find that certain operators are non-local, and also operators that everybody knows, like the Parton distribution functions. They have operators which are separated by light-like distances. And this comes from the fact that in this case, certain derivatives are not really suppressed because it's exactly the derivatives that contain large energies. So yes, there are theories which have certain controlled non-localities in them. But I'm sticking for the moment to the simple ones where this does not happen, where I really integrate out some very heavy particle. This is in principle, this propagates such a short distance and then goes away. It's highly virtual, so then I can always expand propagators in the series that are old and then good. So we do the counting now. So we said d minus 2/2 was our result for the field. So then phi squared is relatively simple. Just d minus 2. And then if I subtract the k here, then I get the d, I get minus 2. And what does minus 2 mean? Minus 2 means that it goes like lambda squared. So this term will have a coefficient lambda squared times something dimensionless. So that is interesting. So if you write the term like this, and you do this Wilson procedure, you should find that this coefficient grows strongly with this lambda. Let's do the next one. For the phi, we had d minus 1/2 times 2 is d minus 1. So minus the d is minus 1. So that would mean this goes like some lambda, still like 1 power of lambda. So these two terms don't really look like what I've promised here, or one they do, but it's negative. Now let's do the phi to the 4th. This is of course just twice this. So it's 2d minus 2. Minus d is d minus 4. Now, what the coefficient is depends on the dimension d. But if you're in 4 dimensions, and then this is 0, and this is 0, d equals 4. And so if you do this integrating out to first approximation, the coefficient should not really change much. You have some dimensionless number that multiplies this. And then let's do this one here. This is the Fermi theory case. So this is twice the thing above here, 2 times d minus 1. I subtract d, so then this is d 2. And in 4 dimensions, this is 2. So that means when you do integrate out this high energy physics, the coefficient of this thing, this should go like 1 over lambda squared. Now, in this Fermi theory, the place where there is really something happening is when you have enough energy to produce the W. So when you integrate out, this scale lambda will pick up this W contribution. So we'll find that this will go like 1 over W squared. And in our tree-level computation, we had this propagator, we expanded, and we found exactly this 1 over W. Now, depending on whether things scale with a positive, negative, or dimensionless, these operators have different names, also from Wilson. So if the K is larger than 0, this is called a relevant operator. Means that as you start integrating out the energy physics, this becomes larger and larger. K equals 0, this is called marginal. And K smaller than 0, this is called irrelevant. What we've seen here is that this 4 Fermi theory operator, this is irrelevant because the K is 2 in 4 dimensions. And that means that if you go to low energies, things will be suppressed by a large scale. That means it's small. So the reason that the weak interaction is small at low energies is not the coupling. The coupling is not weaker than the electromagnetic coupling. The reason that it is small is that at low energies, it's mediated by an irrelevant operator. There's already a nice result. You explain why the weak interaction is weak. The reason is this is 1 over mw squared. It's the fact that it's an irrelevant operator. When you do 5 to the 4th theory, maybe Matt already had 5 cubed at least. We can do 5 cubed. So what is 5 cubed? Minus 2 half times 3. See, when I haven't prepared my exercise, it becomes much harder. 3 halves d minus d is 1 half d minus 6 halves minus 3. And so in 4 dimensions, it's also minus 1 d equals 1. So that is a relevant operator. So this 5 cubed would seem to increase as you go to low energies. Now it's fun to change the dimension. Let's go to 6 dimensions. Then it's 3 halves minus 3. So in 6 dimensions, it's marginal. And people like marginal couplings. So that's why often people study this 5 cubed in 6 dimensions, because then it has this marginal. So now, if you go to the standard model Lagrangian, then you can ask now which of the operators in the standard model Lagrangian are irrelevant, which ones are marginal, and which ones are relevant. This is now a very advanced question. So, how many irrelevant operators are in the standard model Lagrangian? Of course, now many operators, and it's sometimes difficult to see, but you can just look at the dimension of the coupling in front. That should give you a hint whether it's relevant or irrelevant. Are there any standard model Lagrangians which have some 1 over some energy scale?
Are there any dimensionful couplings? Is another way of saying the same.
Yes, and of course dimensional can go both ways. It could be like this, or it could like the other one. So are there any dimensionful, or you can do the irrelevant first and the relevant marginal afterwards.
Pretty sure they're all marginal.
Yeah, it looks like, I mean, all the couplings you kind of know about.
Yeah.
They seem to be like the electromagnetic coupling dimensionless. So that must come with a marginal operator, QCD coupling dimensionless, SU2 coupling dimensionless. So it looks good. Yukawa couplings dimensionless. Anything else? So is there anything that has dimension in the standard model? There is one term that has it. Yeah, the Higgs. So the Higgs somehow is very weird. All the operators are marginal. And you would say, well, for good reason, because the other ones are irrelevant. If you have physics at a very high scale, they would come with the couplings which go like 1 over this very high scale. So let's say there's a W prime particle and U heavy particle, then the operators generated would have a 1 over MW prime. So they would have very small coefficients. They might be there, but we usually don't write them because we don't see them because they're small. And in principle, we search for such operators. But then there's one weird example, namely there's a term like this for the Higgs. And it's not direct, it's this mu squared times phi squared, so it's not directly the mass, but it's in the potential, and so there is a mass scale. And of course, according to this logic here, if you integrate out the high energy physics and the higher heavy particles, once you integrate out, instead of a 1 over MW or 1 over W, you should have a positive coefficient, and this is called the hierarchy problem. And so people were confused why the Higgs mass is so small. With this argument would say the Higgs mass should be roughly the scale of new physics times a dimensionless number. And this dimensionless number seems to be very small because the Higgs mass is this 125 GeV, but we don't see any other new particles at this scale. So it's interesting that we see small. And I don't know why that is. And of course, you can come up with mechanisms which somehow ensure that this is small. So supersymmetry would have been a popular mechanism, which would have allowed you to protect this from some quantum corrections so that this would not happen. But it doesn't seem to be the explanation either. So this is an interesting puzzle in the standard model. Good. And so the fact that we don't have irrelevant ones is maybe not a so this is a surprise. This is maybe not a surprise. If the new physics is at the high scale, these additional terms should be suppressed. So then the theory looks like only marginal operators. And in the traditional sense of renormalization, you're only allowed to write down marginal and relevant operators. If you do this, then the theory is called renormalizable in the classical sense, meaning that you don't generate any new operators when you renormalize, you sort of stay within the small family. But I think once you accept that it's not the ultimate theory of nature, you should accept that the Lagrangian will have all kinds of other terms. These other terms are maybe small if the new physics is far away, but in principle, we should write them down and keep them. And we'll come back to the standard model effective theory after we've done our simpler photon world. Good. So now we know how to count, and that will be very helpful when in the photon world we'll have to write down our effective Lagrange. Now, since these path integrals are hard to compute, the way we compute is, as I said, this is from the bottom up rather than trying to do the path integral. Sort of try to anticipate the result, and we'll just write down at low energies the most general effective Lagrangian we can write down. And this is called continuum. So in order to do this, you basically, in the first step, just identify what particles are around at low energies, and then you will start writing Lagrangians for these particles. So for Fermi, you have protons, neutrons, electrons, and neutrinos, and then it's perfectly fine to write a Lagrangian for these fields. If you're at a bit higher energies, you start seeing quarks and some substructures, then you will use this. So identify the degree of freedom of the theory. So what are the fields that are needed at low energies? If you do QCD at very low energy, what you would see is pions, protons, things like this. And so then you would really write down a Lagrangian for pions and for protons. And people do this. This is called chiral perturbation theory or chiral effective theory. In our beautiful photonia world, we will know the only degree of freedom are photons, and we write the theory for photons. So then, once you know this might need experimental input from the QCD Lagrange. It will not be obvious that you find pions and protons, but you can look in nature in case you can't compute it. Once you have this, so you write down the most general effective Lagrangian. And of course, this effective Lagrange, there are infinitely many terms we can write down here, but we will only include terms up to a certain dimension at a given accuracy. So what we want is, I want to have some expansion parameter lambda for the terms in fact, in this non-relativistic case, if you do this, then at the lowest order, you find exactly the effective Lagrangian that you use in quantum mechanics to compute the hydrogen. We'll see what we get for photonia. And now, what is the difference to the framework by Wilson? In Wilson, we just chose some lambda, and we simply integrated out everything above lambda, and we could have sort of manually steer this. In this framework, we write down a continuum field theory without the cutoff, and so it's not immediately clear what lambda is. Here, lambda will be some physical scale. So it will be the scale where some new degrees of freedom will come into play. In this Fermi theory, lambda will be the W mass, because if you go up to energies like the W mass, you start producing. So there are new degrees of freedom enter. In our effective field theory for QED, this lambda will be the electron mass, or maybe twice the electron mass. It will be at the energy where we start producing electron-positron pairs, and where we sort of are no longer in photon land and have to change things. And now there are more steps. And the question how many more steps you can do depends now whether you know the full theory or not, and whether you can compute in the full theory. It could be that the effective theory program more or less ends here. If you do this chiral perturbation theory, you say, okay, I want the Lagrangian for pions. You write down the most general thing compatible with symmetries, and then that's it. All the Wilson coefficients you will get, you have to somehow take from experiment or from some numerical simulations. It's hard to directly get them easily from the full theory, even though you know above it's QCD, and in principle this is all good. Now, in cases where you can compute, you could determine these by doing a matching. Matching is a technical term. Yeah.
When you say we write down the Lagrangian that preserves symmetries,
Hmm.
do we ignore the fact that most of these symmetries will be broken by, as we previously discussed, or do you only have to respect the ones that remain?
Well, if there's symmetries, they are. It depends what you mean by broken. So
Yeah, not symmetry breaking, but
so this traditional symmetry breaking means the theory has a certain symmetry, and the theory has the symmetry period. Then also the low energy theory will have this symmetry, but it might not be obvious that it has the symmetry because, let's say, the vacuum doesn't have the symmetry like this. So there are effective theories like this chiral perturbation theory, where if you go to massless quarks, then the theory is symmetric in up and down quarks. This is called this chiral symmetry, and you can rotate left and right-handed. This is the symmetry, and this is symmetry that is spontaneously broken. And however, the low energy theory will have this symmetry still there, but one says it's non-linearly realized. So the pions can be viewed as the Goldstone bosons of this chiral symmetry breaking. So what you in essence do is you write down an effective Lagrangian for these Goldstone bosons. But the symmetry is still there, and the symmetry at low energy is then a shift symmetry of this Goldstone boson. So it's realized in an interesting way, but the symmetry is still there. But it should not break. I mean, let's say you have parity symmetry in electrodynamics, then there's absolutely no reason why at low energies where we're in photon land should also have parity symmetry and charge conjugation symmetry.
So the examples you mentioned here aren't, as far as I know, affected by introducing this scale. I mean, more.
No, so now we will not introduce the scale.
Okay.
One big advantage of this is we don't introduce the scale. We simply write down a Lagrangian, let's say only for pions.
Okay, so for determining which symmetries we care about, we ignore the fact that some scale will eventually emerge.
I mean, what will happen is that we will order our terms in this effective Lagrangian, and you'll basically find that this effective theory starts breaking down, that all these higher order operators. So this lambda will now be some physical scale. Let's do the one example that we already know, this Fermi effective theory. So then the lambda is basically the moment, the external moment that we identify. And you write down all these operators with P, they have derivatives. And you'll find as you start approaching the W energy, then of course this P becomes as large as this, and then all these higher order terms will start contributing. So you'll see that your computations break down, but you don't really have to put a cutoff, a hard cutoff. This is a bit weird in this continuum effective theory, and we'll see this. So if you work with this pion Lagrangian, people don't put a hard cutoff. But of course, that means you kind of integrate up to infinity, and you'll find all kinds of divergences when you do this, but this can be renormalized. And so that's it. So the coefficients here are, of course, these Wilson coefficients. And the way we do this matching is just by computing the same quantity in the full theory and in the effective theory. So this is if the full theory is known. So you not write it since the blackboard is small. So if you know the standard model, and we've done this, then you can write down the diagram with the W, and you can compute the beta decay with the W. And then you can do the same computation in this 4 Fermi theory with this operator, and then you can adjust the coefficient of this operator so that it reproduces in the low energy limit the full theory computation. So this is called matching. And this we just discussed. Usually we will not put a hard cutoff. We really treat this as a continuum theory. But of course, since we then integrate up to infinity, and since we have operators with derivatives, there will be divergences. And so you have to somehow regularize the theory. You could use a cutoff, but again, cutoffs are not so nice. But when you do these computations at the loop level, you need to regularize, and usually one uses this dimensional regularization. Who of the quantum field theory folks has worked with dimensional regularization? Not so many. This is kind of a weird procedure, and it's something one add a lecture or a tutorial on it. So is instead of computing in 4 dimensions, let's compute in 4 - 2 epsilon dimensions. Very weird if you haven't done it. But usually in lower dimensions, things are more convergent in the UV, because you have an integral UVK, these loop integrals, and then some integrand. If you make this t smaller, you manage to tame divergences, and then there needs to be an explanation how this is possible to even compute this, but one can take such an integral and actually make sense of this. And then the divergences are regularized. So then things which simply don't exist, some integrals in 4 dimension, they become so you get 1/epsilon poles in these computations. In the third lecture, I will show you some examples. Maybe that would be a point where I could explain this dimensional regularization to an example. So you get this 1/epsilon poles. So you get finite things, but as epsilon goes to 0, as you want to go back to 4 dimensions, you start to diverge. And then again, const QFT, but it's something that one has to do in any QFT. These divergences will always arise. In fact, even in quantum mechanics, once you start adding these correction terms to the hydrogen atom, also there you find these divergences, because when you do this, for example, this relativistic correction, this p to the 4th, this can already give problems. Also, the corrections to the potential give problems. So somehow these ultraviolet divergences are hard to avoid, and so then one needs some way of regularizing this, maybe an ultraviolet cutoff, or more elegantly with this dimensional regularization. So that would then be the next step in the program, if we can compute. So these Wilson coefficients that arise when you start doing this matching, you find that there are these strange divergences arising, ultraviolet divergences. These can be tamed by computing in p dimensions. And then you find that these coefficients depend on this epsilon, and they will blow up like 1/epsilon as you make epsilon smaller. Then what one does is you can absorb these divergences into renormalization constants. Like that. It's not entirely unique how you do this, and when you do this, there is some scale mu called the renormalization scale that arises. And so doing this, you can absorb these divergences away, and you can work with finite Wilson coefficients, but they depend on scale. And then once you have this finite coefficient, one can solve an evolution equation. So this process, this weird scale mu arises. Physics cannot depend on this scale mu that arises here. And so that imposes some constraints. And this gives some evolution equations or the new dependence. So the new dependence must behave in a certain way that at the end the physics result is independent. We'll do this in much more. So this entire thing is the third lecture, so don't be worried now at this point. So there are equations which arise, which you can solve. And these equations, you can do an evolution in this mu. You can start with the mu at the high scale, lambda, so this is the hard scale. Then you solve this dd log mu and you evolve down the low scale where you the physical matrix element live. And as we'll discuss, in doing this, resums the logarithms of lambda over e. So if you simply compute this matching, you'll find that these coefficients have these logarithms of lambda over e, and these can be large if these are very different, and this can destroy perturbation theory. Using this technique, this can be restored. And so then the last step, which doesn't have space on the blackboard here, is to do the low energy computation. In our photon effective theory, we'll have to do the matching. We could, it actually turns out this is nice because there are no divergences and no running. But at the end of the day, you can compute the low energy process. And of course, this will involve these operators and then some matrix elements at low energies of this, which give scattering cross sections or whatever you want to do. Good.
So would it be fair to say that Wilsonian effective field theory kind of forces you to regularize using a cutoff, while continuum allows you to choose something more appropriate, or is it more subtle than that?
Yeah, and the Wilsonian sort of the standard cutoff is this lattice regularization. In order somehow destroying gauge invariance would be a complete disaster, and it's very hard to. It's not a problem in principle. You can destroy symmetries in the sort of quantization, and you can try to restore them. But it's for gauge invariance would be a very bad idea. So yes, it will break Lorentz invariance, and but then if you make the cut, well, you'll find that these breaking terms would be small. The nice thing about this dimensional regularization, and the reason why this is basically the only thing that people use perturbatively, is that this is really friendly to all the symmetries, to almost all the symmetries, because it's just changing the dimension a little, and you can of course write down a gauge theory not only in 4 dimensions but also in 3, and actually also in 4 - 2 epsilon dimensions, and have it invariant. The only thing that doesn't work so well is things that involve gamma 5, because gamma 5 is a specifically 4-dimensional quantity. So there are also here some problems and some technical difficulties, but much less than with a cutoff scheme.
So I think I maybe should restate my question as.
And I don't know how to do with the Wilsonian. You definitely need to have a scale that can be a lattice spacing, or it can be this cutoff. And I don't know of a good way to do this without breaking the symmetries.
So for Wilsonian, this scale that we have to introduce as part of the process that you laid out here, does that already regularize, or are there some cases where we still have divergences we then need
No,
to take?
with this lambda, everything is fine.
Okay.
I mean, all these divergences have to do with the fact that you go to very high energies. And in some sense, you can say, well, this continuum effective theory, anyhow, is only supposed to be valid at low energies. So we could just put a hard cutoff at this MW here, and it would be fine, except that it destroys many nice properties. While if you do this dimensional regularization, you don't introduce any additional cutoff scale, and all these things get very simple. Also, the counting gets simpler if there's not this cutoff floating on. So the problem is if you would use a cutoff regularization, you would now have the cutoff lambda, and you would also have the scale of new physics. And so there's two scales around, and you have to discuss both of them. While in the string dimensional regularization, there's no additional scales, and it's kind of much nicer. Good. I think I'm basically done with this lecture one. Maybe some final remarks in the last 3 minutes. So the question is, of course, why would you do all this? Such a long program and then all this matching. Why not just take the full theory and do the entire computation rather than first writing a lower, then doing all this matching? An important reason is this resummation of logarithms. So if you just use the full theory, it will be very hard to control these logarithms here. And basically, you'll find that if you use perturbation theory in a system with different scales, it will simply break down. So you're forced to do something like this in order to use perturbation theory. Even if the coupling is small, it will break down if you don't do this. And then, of course, also the hydrogen atom has shown this. If you would like to use QCD or the standard model to compute hydrogen, you would never get a result. And there is actually no computational method known to mankind that could simply give you a result for a hydrogen atom. If you simply, for example, we try to do the entire hydrogen numerically on the lattice, that would not work because you have very different scales. So you need extremely fine lattice spacing, which accommodates both the 1,000 or 10,000 times larger scale and the other scale. So often you have to separate these things. If you separate things, you can also separate the perturbative and the non-perturbative. For example, in the hydrogen atom, there are effects associated with the proton. These are non-perturbative, but with this approach, you can separate them out, compute them separately using maybe a lattice simulation, and then the rest is perturbative, and you can do it in a different way. And the final thing is that often when you do this at low powers in lambda, you can have additional symmetries. For example, in this theory called heavy quark effective theory, this is about very heavy quarks. You get an additional spin symmetry at leading power in lambda. Or if you do this chiral effective theory, you can get this chiral symmetry approximately. So there can be additional symmetries. And yeah, that was it. And it's also a general framework. You maybe not be able to do all the steps, but even if you don't know the full theory, let's say we don't know the ultimate theory of nature, which we don't do, then this program gives you a way of writing down the Lagrangian. You can say, which are the particles I know, upwards, downwards, Higgs, etc. And then you just write down the most general Lagrangian, and that will be the standard model. So it's also a general framework to write down theories if you don't know the ultimate theory of nature, which is always. Okay, that's all for today.
You guys still have a question? One go. Oh, okay, then let's have lunch and come back after an hour's lunch break.
Sorry, are you starting at what time again?
An hour from now.
So 1:30.
Yep.